Today I want to look at crashing. So in my language I recently added strings, which works. Like this is a program that outputs hello world. But crashing doesn't work yet, and that prevents some other language features from being implemented. So yeah, this is the Zig VM that runs the code. Today I want to actually just implement crashing. So there's a built-in crash function, in theory at least, that takes a string and it crashes. It doesn't work though, so I think somewhere in the compiler there's still a to-do. Yeah. In here, converting something to the pudding. Okay, so crash should be converted to pudding built-in.crash. However, it just says unreachable. There is unreachable here. Well. Okay, so there's an uninitialized expression. I'm not sure what to do about that. Or where that is even created. Hang on, let's see. The pudding is built from the yogurt, and in the yogurt we do have an uninitialized expression. Indeed, we do. Well, where's that created? Do we have a something to yogurt compiler stage? Yeah, we do. Here? No, not really. Oh, in the cast maybe. Not in here. I think we can just remove that. And I mean, if that does exist, then that at least tells us where that is being created. Yogurt opt.uninitialized. Boom. Where does stuff fail? In the cast. Didn't I just search for uninitialized here? Oh, look for unreachable. I see. Okay, so if we are casting from the never type to something, then that doesn't work. I mean, I guess, yeah. Let's instead just crash there. So let's say this is yogurt opt.call. So more specifically, this happens if you have something that can never complete, such as a return statement. Well, we don't have return, but a crash, for example. And then you try to assign that to something else, to an int, for example. That should type check, and that should work. But during runtime, we never create an int. So never this never type that the crash returns, that can be assigned to everything. When casting that, I think we'll just cast yogurt opt.call the never built-in, and that's it. Yeah. Where the callee is the yogurt callee built-in of the yogurt built-in.crash, and the arguments are something. I guess some slice of other string, basically. Yeah. That is body.push yogurt out.string. Let's say an empty string of the type string. I see yogurt up needs a yogurt type. Oh, of course it does. Yogurt type.string, I assume. Yeah. We no longer need uninitialized. So then in the yogurt we can just remove the code that deals with that. We can just remove this one. In the pudding, let's remove that as well. And then in the yogurt pudding, we no longer need to map that. All right. Yeah, we're slowly getting there. So primitive type string. What? Oh, I see. I think string doesn't need to be a type in here. I think. I'm not entirely sure. Let's see. The egg comes before that. Does the egg have... The egg uses plum types, and these don't have... Yeah, string is just a normal struct. Yeah, there is no extra string type in here. So then in the yogurt, we don't need to add a string type here. No, we'll just have a yogurt type string. If that, maybe not even that. I'm wondering though, is there, I thought there were like some predefined types. Yogurt type int or something. No? Okay, maybe not. Well, in the something to yogurt. Egg to yogurt mod. Yeah. Yeah, then this is not something that we'll need to check. We have bytes, we have ints, we have types, and we have arrays. Yeah, that is correct. Yeah. And then in here, that is just a struct. That was like string type. type string dot compile, I believe. All right. Then in the pudding, next compiler stage, we no longer need uninitialized. We no longer need, oh, these have yogurt types, I see. Yeah. And then in the pesto, this is no longer a thing. Neither was this or this. Clean. And then yogurt to pudding. Here we do put uninitialized things somewhere. Oh, I see. But this is just a placeholder, so we could just as easily put there. I don't know, parent. To adjust the hash function manually. Sure. I mean, dropping arrays is actually useful. That's something I should be able to do. Oh. Okay, yeah, now we're getting somewhere. Crash to pesto. So a crash built in, it already has a message that has been lowered. And I think it should just be a pesto built in dot crash. So then in here, in the fun ground builder, when compiling a waffle expression, well, we want to, how does crash, the crash instruction actually behave? Yep. It first pops a length and then an address. Okay. So, yeah, I think the arcs contain a length, an address in the length, basically. So we'll need to get those members, basically. I think there was like builder.member, maybe. Maybe not. Oh, you need to manually like pop things and so on. Okay, I mean, in our case, let's just compile the arguments using the builder, and then we emit a crash instruction. And this is the message. Yeah, that already has the correct layout, which is an address and... Oh, hang on. That's a string, is a plum string consisting of pointer, start, so we have a string. In reality, that is just a bunch of UTF-8 bytes. And that is just pointer, start, and a length. Pointer to some buffer that then consists of a ref count, a length, and text bytes. Yeah, so like this. So on the stack there's the pointer, the start, and the length. Now what we do is we do builder.pop and builder.push from stack. Push get from stack offset 16. So then the stack is just pointer, start, len, and then the pointer again. Let's push 16, push the literal 16, so push 8 to 16. And then add those together. No, that is like way too low level here for that. Let's see what the waffle looks like. In the waffle, we do have the waffle crash thing right here. Alright, and that just has a waffle expression. I mean, then again, like, these are kind of documented in the constructors below, so. Yeah, crash just has a waffle expression, and I think you create that using waffle crash with a message which is supposed to be 16, not a buffer pointer plus len, because that's really what we want here. Yeah, and then in waffle to ground we can just know, like this is not a plum string. The message already has the correct layout for the plum and for the crash instruction. But then when converting to the waffle, yeah, this is where we need to adjust the crash stuff. Yeah, this is just 2 integers, that's totally fine. Waffle body crash without a message. Then we have waffle crash. But this is... this was a pesto thing. Yeah, I think what we need in here is to actually get, well, yeah, to create a waffle crash of a pointer, so of a waffle aggregate first of all. Of some other things. Alright. And what other things? Well, first of all, a pointer to the message, so that would be args.get. Convert the plum string to buffer pointer plus len. And here we have the waffle add. From that plum string we get add offset 16, add offset 0. We get 8 bytes aligned by 8 bytes. That is the pointer to the string buffer. I mean, we could just compile stuff into a function. I don't know. No, probably not. No. Yeah, that's fine. We get the first 16 bytes, then we load that. Oh, no, that's the pointer. We just add 16. And then we'll get the length. So this is the buffer pointer. Then the pointer to the bytes. Pointer to buffer. String layout is this pointer start len. Although not quite, because they are sorted alphabetically. And this is really called buffer, so this is, it goes like this. Yeah. We can also see that in the, well, first have a pointer, then we have the length of the string hello world, and then we have the offset. Yeah, so the length, pointer to buffer is at offset 0, pointer to bytes is a waffle add of that pointer to buffer. And the buffer really just points to this right here. Waffle add pointer to buffer, a waffle int of 16. So then we have a pointer to the bytes here. And then the length of the message that we want to crash with is just args 0 dot at offset 8. And let's pull that out and call that message. All right. Yeah, and then we crash with two things in here. Pointer to the bytes and the length. All right. That makes sense. This doesn't work because it needs a list. True. Taking so long. Wait, what? Whoa, what's going on here? This is a lot of stuff. What? What the hell? That's what, like 39 megabytes in size for some reason. 3 times bigger than the compiler. I mean, we're only crashing, you know, it's not. What do we do in here? Compile the message and then we crash. Not sure what to do about that. Let's look at the top of that file. Nope. Can you do like, I mean, I can, oh, I can do hex dump and type that into ES, maybe. Yeah. All right, so let's see. We start with pushing let's print the waffle maybe. Oh, of course that doesn't work, because we are missing some stuff here. You don't handle waffle expression kind of lower byte. Probably don't. Yeah. All right. That's not too bad, isn't it? Okay, let's see. We have this playground main function. Yeah, has a parameter, sure. Then it does this, which means it allocates, well, 16 plus 13 times 1. Yeah, this is enough for, this is a crash probably, and this is the 16 bytes for the reference count and the length. Then in that we store the reference count of 1. In the pointer plus 8 we store the length, aka 13. And then in the pointer plus 16 we store the actual bytes. And then we crash with this aggregate. It has two parts. First of all, it has it has this one, you know, an aggregate, which represents the string, I believe. You know, the pointer and the length and the start position. And we get the member at position 8, aka the length, the 13. This should just be 13. And then this right here is the same string. We take the member at 0, 8, that would be this one, just the pointer. We put that in an aggregate with 16 and we add that. Alright. So then this basically is just calling crash with those. So this crashes. And then we cast that never return type of that to, you know, a string. And that results in an aggregate. Now that is interesting. Oh yeah, that makes sense. Yeah. And that is this part right here, where we just create an empty string, I guess. So we allocate only 16 bytes for the overhead. Well, bro. Then we store a 1 in there, we store the 0 in there, the length, and then we store the bytes, aka nothing. And then we crash. Yeah. Using that pointer and the other pointer plus 16 and then some nothing. Okay, why is that so much bytecode? First we create a string. So we push a 16, alright. We push a 13, which is the length of the string, and a 1, that is the size of a single byte. We multiply those, we add 16 to that, that's the length of the string we want to allocate. We push an alignment of 8 and we allocate memory. Boom, this is just for allocating memory for the string. Then we push 0, and we push that same address to the stack again. We push a 1 there, and then we store the 1, aka the reference count. Then we push the address again. We push an 8. We add 8. That's the length. Yeah, we push 13 to the stack and we store that there. Okay, and now comes the actual content of the string. We push the address. We push 16, we add that. So address plus 16, the place where we want to store the bytes. And then we store the bytes. 13 bytes to be precise. And then here are the 13 bytes. Fair enough. And now we no, I'm not entirely sure what's going on. Now we're pushing that same address again. And the length and the cursor, and then we pop 16 bytes, leaving us with only the address. Okay, sure. Then we push the thing from 16 bytes back on the stack. And we add those. Oh no, we push 16 and add that. Okay, that's the position of the bytes in memory that we want to crash with. So then we push the original pointer again, and the length and a cursor. Then we pop 8 bytes. We pop 8 bytes below the top 8 bytes, leaving us with only the length, and then we crash. That makes sense. So far, so good. Perfectly reasonable. Now what do we do? This just looks like garbage, to be honest. I mean, C0 pushes something, or pushes a byte to the stack, I think. 1. Why? And then we call something that is actually reasonable. C0 and F2, what are those? Oh, I see, C0 is padding, 1 byte of padding for some reason. Okay. And then we call this one, which is a really high location. And let's output the ground, you know. Not the ground serialization, just the ground itself. Dang, that is actually super long for some reason. Why? I don't get it. Wow. What? So we are popping a lot of stuff for some reason. And I mean, what? What's going on here? Crashing just compiles the message. Yeah. Why is that this crazy thing? Oh, is there like a stack underflow maybe? And then we need to just have so many pop below top instructions kind of until we kind of wrap around. That would be kind of insane. Oh, maybe that's the case actually. Okay, so in the somewhere we have this, what is it? Like this model of a stack. Is that here? Or is that in the waffle? Actually, I think that's here. Yeah. Yeah, okay. The builder is a ground builder. A fun ground builder, sure. I think because we have switch statements that actually have separate stacks, basically, rather than doing that in an ad hoc way where we, you know, like, I don't know, in the switch we say what's the stack size at the start of the case, and then for each of the case we kind of reset the stack size. That's not super elegant. Instead, I think I'll have a separate stack model kind of thing. And that is just mapping, I guess, and size. Yep, and I need to pass that around separately from the function builder. And like, do I even, what? Why do I have two of these? Fun ground builder, add mapping, fun ground builder, fun ground builder, fun ground builder. Do I even use the ground builder? I do for some reason. Oh yeah, but like, no, not really. What the hell? Maybe just remove that. have stuff like this. Oh, I see. Hang on, it has instructions. It has patches. It has the waffle. Yeah, and the only thing that's different here is that it has a stack. Well, mapping, it previously had a stack size. Which, I mean, let's move that down here maybe. And the function, we can pass that around separately. Then we can get rid of this. Yeah. I want to have something like that. And maybe have stack mapping be that, have that be a pointer to a map, so that this can be shared among different stack models. Yeah. Bad thing is these kind of need to work on the instructions as well as the stack model. I don't like a lot of that. basically a control flow ground builder. It's getting hacky and hacky, I believe. Just contains, you know, instructions. And patches and a stack mapping and a stack size and a function, and I mean, what does it not contain, you know? But then basically I want to be able to have a first class, you know, split on a control flow ground builder. Or maybe it's also like this has crashed. But then also join of multiple ones. And just then make sure that they have the same stack size and stuff like that. I would like this. You know, this is just something for emitting ground instructions. Simple. And then here we have a function ground builder, compiler really. Builder. I don't know, it contains, let's call it builder, sure. Parent builder, which is a ground builder, so it doesn't need this. And it just also keeps track of the function that we're currently compiling and the waffle. And then we have a control flow ground builder that also has a parent, which will be a fun ground builder. And it just keeps, and in addition to that, it just keeps track of the mapping on the stack ID to int, and also the stack size and whether we have crashed. Phew, yeah. It's a bit more layered and nuanced than before. So that most of the functions here will just work on the control flow ground builder, which will in turn append stuff to the fun ground builder, which will in turn append stuff to the ground builder, which will in turn append stuff to the instructions and the patches. All right, so we have control flow ground builder, and we can split that, giving us another control flow ground builder with the same parent, but with a different stack mapping, first of all. Not really, to be honest. Like, basically a copy of the map. I think I have like a copy function, so yeah. The stack size is going to be, the builder stack size, but from now on it's independent of that. And has crashed will just be builder has crashed. Or rather false, I guess. Yeah, the default is false. So this is to do, join control flows. Okay, and we can add a mapping to a control flow. Or let's just call it flow ground builder mapping. And that just does builder.stack mapping, which is already immutable map.put. Yeah, and these work on flow ground builders. And instructions is not a thing. Yeah, true. Because this really just pushes instructions to the parent. Let's call this like context. Yeah, make it so that this actually contains the ground builder and context. Yeah, that makes a lot of sense. All right. So this really just does ground.push. And on this we need a push instruction. I mean, I guess it's fine if we just do ground.instructions. Builder.ground.instructions.push. I need to add a, oh no, this is already a reference, so clean. All right. And then for the crash instruction, all right, I can, instead of setting the stack size to something weird, I know where the crazy padding comes from. Instead, just says has crashed. That's not perfect. But yeah, should work. Can't type. Yeah, has crashed, true. Amazing. And then here we can just do if not, like if builder.has crashed. then return. Because then we don't need to emit anything. That is super cool. Yeah, I think I didn't get all of them, so let's see. We have these. Yeah, in here pushing a single value of 8 bytes. Still don't want to do anything if we have already crashed. Well, you know, these kind of things. I think, yeah, rather than that, I'll just want to assert that I haven't crashed yet. That's a cleaner way of dealing with that. Actually, in the patching, I think I don't need that. Yeah. All right. All right. So this one compile, first of all, here. Because now the waffle to ground. We create a ground builder, that makes sense. Yeah, it doesn't contain the waffle though. For every function, we compile the function using the builder and context, which is the waffle and the function. And this is a ground context, or whatever I called that. Let's see. Yeah, ground context. Not really. Yeah. All right. Yeah. And then in this compile function, that just takes a builder and ground context. And what we do here is we build a flow ground builder with the ground being the ground. So we don't need these. Has a stack mapping, which is empty. It has a stack size of 0. It has the context. All right. That does seem reasonable. Then it compiles the function body using that flow ground builder. Hell yeah. And then for every local variable, we do builder.align to we compile the expression, and then if builder dot has crashed, we'll just break from the loop, because if there's a crash, then the rest of the function body, the rest of the waffle doesn't even need to be compiled anymore. We could already do that directly in the waffle. Maybe that would be more, like, even cleaner, you know? Alright, then we align the body to something, we compile it. Alright. Yeah, and then this is also like if the builder, if it hasn't crashed yet, then we pop below the top. Pretty cool. Okay, to come to think of it, this is quite, I don't know, cumbersome, I would say. So I think instead we'll just, I think returning nothing is fine. You know, except for like jumps. Yeah, I really want, we have already crashed. All right. Yeah, then we don't need these. And yeah, we don't need these. But I'll add like a general to do. Do the builder, maybe. Do the crash, remove code after crash optimization already in the waffle, so we don't just silently do no ops here. All right. So yeah, this is actually a flow ground builder, and that's even cooler than a fun ground builder because you can kind of split that. Yeah, and then in the switch in here, so first of all, at the end of a function body, I think the popping, we only want to do that if the function has not crashed. Yeah. So if builder dot if builder dot has crashed, only if it doesn't, if we don't crash yet, then we pop stuff below the top. Otherwise we don't care about that. Okay. And then also in the switch we can do things more elegantly, because here we can say, well, rather than doing this, quite small, I like that. And we can create a child builder. So here we can say builder.ground.instructions.len, and then in here we can say builder.split. And then we don't need to reset the stack size here. Yeah, and then say there's just a list of flow ground builders. Yeah, we compile the case. We push an end jump and we push the case builder into that. Yeah. We fix those, we patch the jump table, and then we say builder.join case builders. And this will actually set the stack size and so on of the parent builder. And what we do here is, well, the context stays the same, the ground stays the same, the stack mapping stays the same, stack size and has crashed though, they are different. So here we kind of make sure that all of the case builders have the same stack size in the end, or that they are crashed. And then in the end, we set our stack size based on that. If there is a stack size, then we just say builder.stack size equals that. If there is none, then we just say that is some weird number and we have also crashed, because then all of our children have crashed. Yeah, this case evaluates to a nothing, but previous cases to bool. Let me think about that. Yeah. Oh well. Let's put the context here as well. Context is just that. Yeah, and align to 80. Yeah, here we can just return 0, I guess. In the long term, I want to model this a bit better, I think. Yeah, don't just, like, especially this part. Have separate fields for stack mapping and stack size that has crashed. That has crashed. Then the others are valid. doesn't seem super clean to have a has crashed field that indicates whether stack size make any sense. This could be an enum properly modeled using an enum. That would lead to lots of more loaded code. Yeah, that's kind of a limitation of doing this in an imperative language and having this kind of mutable builder that you pass around. I think if at some point I make the Plum compiler self-hosted, I may actually turn this into an enum and then have the split function and have the kind of instruction emitting functions return a new value of builder. Well, not have that, but instead have them return some sort of maybe or option of a builder that you can then kind of directly try or bubble up if that crashed. Maybe something like that. All right. So instructions is not a field here. Context field is missing. True. All right. Now back in the mod file, and the switch to be precise. Yeah, here we compile the individual cases, although these need a mutable builder. So jump placeholder. Yeah. All right. Okay. Yeah, this crashes memory. That is, yeah, that is true. Oh, look at this. This crashes. Hang on. Yeah, this crashes. Nice. How's that implemented? Let's look at that. That would be in the main file, I believe. No, in the root file. Yeah. If there's a crash, then it should say crash, and then the crash. Oh. So build that, make run that. Yeah, this crashes, and then we have no idea of what memory needs to be freed or anything, and that makes total sense. Unlike Zig, Plum programs are not memory safe in the case of crashes. Yeah. You know, Zig has error defer, and then things work generally, but no, not in Plum. All right. Yeah, this is fine. So using that, just because crashes are now possible, I think we can do even better than that. We can now, yeah, return a string, but I don't know, create a list of 1, 2, and 3, and that is backed by an array, by the way. And then push a 5 in there. A couple of times, because why not? And then get the length and format that. So formatting an int is something we want to do. And pushing something to a list. In general, like a list function that takes items and a push. Oh, we have that. Oh yeah, the list type. Just see what happens. Yeah, string, true. Don't need that. Alright. So something doesn't work. Let's look at the egg, I guess. That's just gonna be a lot of code. Well, when converting the yogurt pudding. The egg to yogurt. This is where the error happens. Something is going wrong. What do we do in case of a crash? We just call the yogurt built-in crash. Well, that seems fine actually. Maybe. Where's that happening? In compile, in to yogurt, on a function, on a body, on an expression, on a function, on a body, on an expression, on a function, on a body, on an expression, function, body, expression. Okay. So let's maybe print the functions that are being compiled here. Yeah, compiling a type, sure. Compiling a body, expression. What do we have down here? Here. Yeah. I do want to go for a walk today, so okay, so we are compiling list of t with t equals int. Let's look at the list function. So here we have a list of an A of type t that returns a list of t. Alright, and a list has an array and a length. So here we have an array, which is generate array of length 8, just filled with A's. I'm not sure about the underscore here. Let's just put something in there. You know, the index, sure. Even though the index is never used. Oh, what is that? Let's maybe look at that in the egg in here. That's linked list. Here, list of t. So there's a type t, int 8, a lambda that takes 3 and returns 0, the original item. Then we call generate array with t equals t. using the length and the lambda. That seems correct. All right. And then we put that into this struct in here. I think maybe this is failing, because it does say like key 0 not found or something. So I think when compiling a lambda, something is going wrong. Yeah. Let's look at that in more detail. So if we have a lambda, then what do? We just put there a yogurt lambda. Well, okay, that is actually quite simple. Oh, hang on, we are not. I'm on the type level. Let's go through this. We have, yeah, this is just compiling a plum type. This is compiling as an expression, I believe. Yeah. Yeah, okay. This is quite a bit more complicated. So we're getting the captured variables. This would be a set containing a 0. And then we are building a closure. Yeah. Where we go over the captured variables, iterate it. We get that mapping. Okay, so the 0. Maybe this is what fails. Maybe. In general, we do add that, though, so. Yeah. 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 Maybe let's print some stuff here. Lambda capturing, and then the captured ones, captured IDs, visible, and then we have just the mapping. Okay, lambda capturing nothing. You sure? The lambda in the list t function does capture something. Something quite important actually. It captures the a, which comes from the surrounding function, not from within this lambda. Huh. Alright. Yeah, this is visible, ID 0, ID 1, ID 2, alright. And then ID index 0 is not in the map. Yeah, we put the fields and the field types in these maps. Fair enough, like, yeah. And then the struct type is going to be a yogurt type.struct of those fields. We push a yogurt up.struct of that struct type. We push a closure of that closure type. Yeah, alright. Yeah. And then in here we have the lambda mapping. Where we just kind of go through the captured IDs. Oh, I can imagine what's going on there. We do captured variables. I think that's not working correctly. Captured variables on an expression. Yeah, that collects the captured variables. On an ID. And then in here, collect captured. Oh, we don't need to do this because this is already a set, so oh, hang on, captured as a list. Never mind. For some reason, it's a list. Yeah, but this one, capturing a body. We go through the parameters, we go through the children of the body, but we never look at the returned ID. So body.returns collect captured. Yeah, like even if a lambda never uses some outer variable within its body, except to return it, well, that still needs to be captured. Hopefully that works. Yeah, okay. Yeah, duping arrays, dropping arrays, that's still to do, but first I'm gonna go for a walk. Okay, so duping and dropping arrays. I think that was just still a to-do, so yeah, let me open the dupe drop free thingy. Yeah, exactly. So duping arrays really just dupes the buffer. Yeah. So this is a yogurt type. Oh no, I see. We are trying to emit pesto. So we can just do something like this, I believe. Increment reference count of the buffer. And the buffer will be the... Oh, hang on. Yeah, the buffer is whatever is at the first position in the value. Yeah, so in this case the type here is actually an array type. Yeah, okay. So this is, let's see, putting to pesto types. Yeah, it's this type here, pesto array type. It's just a struct. So from that struct we can get the member. The member named buffer. That's this one, and that's a pointer to the underlying buffer. And then we can just increment the reference count of that buffer, and then we are done. Pretty simple. Alright, and dropping arrays will be a bit more complicated. We'll get the buffer, we'll decrement that. But then, if the reference count is 0, then we'll need to do some stuff. And let's look into the array build-ins for that. So there's array set. There was something that dropped the entire thing, I believe. Yeah, array len. it drops. Oh, there's a drop buffer. That's exactly what I want. Oh, and we can just get the pointer. That is, like, semantically, that is a bit cleaner. So let's do cube buffer, and then in here drop buffer. Yeah, and the item type is just, well, that this, that this type is an array type, but that may be recursive, so we need to extend that. Hang on, what's going on here? Yeah, extend it one level. We know that's an array. So something like this, perhaps. Yeah. I mean, what do we do in here? I would just get the item type. Well, that's convenient. How do we do that for the built-ins? Compile array get and so on. And this needs a yogurt type. See. Yeah, okay. So I guess this is... Oh, that's the way to do that. This doesn't work because that's not a thing there. Well. Yeah, it does work for structs and enums. Okay, so we know that is a primitive type, I believe. Yeah. That's not a thing. What? It has var, it has primitive. That should work. And then inside that primitive type it has an argument. So dot args get 0, I guess. Let's just set that directly, sure. Ooh, and kind of do that, I guess. Let's see. Yeah, drop buffer doesn't work because this is the signature, it has a plum type. Alright, so we get something and then we want to convert that back to pesto. But no, hang on. That's an egg thing. Oh, we want to compile it. Is that what we do here? Yeah, we compile this. All right. Yeah, tube free. We just ignore that. Yeah. Dupe buffer is not a thing. Okay, but drop buffers. That is weird. Compile drop buffer fun. Compile drop fun. Where's the builder? Here it is. So where's my drop buffer? Not in our wrong builder. We want this one. Yeah. Okay, so we have dupe and drop, but no dupe buffer. Yeah, let's call that buffer. I think that's a bit cleaner. Yeah, we don't need the type because that really just is builder dot. Well, first of all, that, and then it's just increment reference point of that buffer. All right. So back here. Alright, let's just see what happens. Dupe buffer doesn't work. We do have... Oh, this needs the pesto. Sure. We can provide that. Right. That compiles at least. Let's see if it works. Okay, so switch cases have different sizes. That's actually interesting. Okay, so we have this waffling expression something. Creating a struct with a start and end and a buffer. Start, end, and buffer. Interesting. What's that supposed to be? Okay, and then we have this one, which is bytes. A struct with bytes with started, end, and buffer. Then we have a pesto expression, call builder and crash. What? That does not seem correct. Do we print the pesto? I don't think so, nope. Let's do that, let's print the pesto. In plum. The pesto, please. Of course, that doesn't work. Every single time I enable printing, I changed something. and forgot to update some stuff, and it isn't type checked until I use it, so that's kind of annoying. Okay, so what else? We have you don't handle store buffer bytes. Load and store buffer item, but not store buffer bytes. That is true. Which is needed for strings. Store bytes to that, to buffer of byte, and then the store buffer at index, no, just that. All right. Okay, quite a lot of stuff. Well, and we are currently failing somewhere. I think when dealing with ints for some reason. Oh, this does contain the entire like length format stuff. Let's maybe simplify the play around a bit. Let's say I don't want to format stuff, I just want to return hi. Okay, still the same error. That's good, actually. Let's also simplify this grammatically. Still the same error, hopefully, yeah. And if I just have a list of 1, oh yeah, different error. Good. All right. Do I even need to like push something to the list, or is that just? Oh, that works. Okay, that works. Sure. Okay, but that's pretty cool. So this has something to do with setting something in a struct in the buffer, which I was unable to test before crashing worked. So it makes sense that there is still some stuff in there that doesn't work. There's just a lot of stuff here. Let's go with this. Let's walk through this from top to bottom and look at interesting functions, I guess. And also see where the array functions are desugared in the pesto, so this makes sense. Okay, generating an array. We looked at that before, that seemed to work, so I'm not going to go into detail here. Then we have ordering, dropping a buffer of ints. Dropping a buffer of an array of ints. Dropping a buffer of array of int items. Something like that. That's not what we want though. Like, no, we don't have that. So drop buffer, where's that called? This actually makes sense. Drop buffer fun. And this accepts I believe we do have some drop buffer of int. That actually seems correct. Is there also like drop buffer of array of int. Yeah, that's not what we want. Okay, so this is supposed to be the item type. Let's make that kind of a bit more explicit in here. And maybe even syntactically like that. And then we call compile drop buffer items fun. Yeah, drop buffer items fun. With the item type. That's also used down here. Alright, and in here. Cool. Yeah. I mean, rather than here we can just do drop of what does this do? Drop needs an ID and a yogurt type. This is the ID. This is the yogurt type. This is the pesto. Let's actually extract the item before. I think it's a bit more readable, a bit cleaner. Yeah. Alright, and then we compile ourselves recursively. Yeah, so this will just call ourselves like that. Amazing. Alright, then where else is drop buffer called? Here with the item type. That's it, basically. Which is surprising to me. Huh. Where does that buffer of array of int come into play? Huh. It doesn't make any sense. Drop buffer of array of int. What? If the type is an array type. Hang on, I'm currently in the dupe case. Yeah, this is the drop. So do we have a drop buffer of array of something? No, because that's not. Or maybe we do. Okay, we do have drop buffer of int. Where else do we call the compile drop buffer fun? Yeah. Okay, so we call that on the item from compile drop buffer fun. We call compile drop buffer items fun. That makes sense. Yeah. That's it. Let's do something hacky. Let's say if the signature contains array and panic bad. And then using the stack trace, we can see where that is called from with the wrong type. Yeah, bad. So we do compile drop buffer fun from drop buffer, and we do that from compile array get. Okay, so let's look at that. Oh, that's in here in array build-ins. Drop buffer. Compile array len of the item type. Okay, and then here. Look at that. No, this is not. This should not be the. We explicitly wrap that in an array. Like, come on. That wasn't even the obvious way to call that function, so I don't get it. Okay, so hopefully now the pesto is a bit smaller, tiny bit. Maybe. Let's see. Well, a tiny bit, maybe. Oh, it does print the egg, I see. So a lot of that is just egg. Including the entire standard library, stuff like that. Alright, let's not do that. Let's inspect the pesto. See if that looks fine. Alright. So generate array, we looked at that. Okay, array len. Yeah, that calls array len of array end. Beautiful. And we have a cast. We have that. We have some casts. We have this drop of closure that contains an array and a length. So an int. Okay. All right. Okay, maybe that's interesting. Yeah, init array, I looked at that before. Okay, this is kind of new, dropping an array, I think. Yeah, that gets the array from here. Oh no, dropping the struct. Ah, okay. Array.set. Really interesting. But just calls something. Not sure what happens here actually. Let's look at that. Array.set. Alright. So this accepts an array with a start index, length, and buffer pointer. Okay. Then an int, the index, and then another int, the item. Okay, and we get the array, the index, and the item. Fair enough. And then we kind of construct a new array of that same array, same index. Same item. Then we call array get. That doesn't make any sense. Array.set. Let's look at that. Set on an array. It does array.array set. This is weird. This is just weird. I don't get that at all. Okay, then what else do we have? We have array get of an array. Okay. Okay, getting something from an array, that takes an array, start, len, and buffer, and an index. Alright. And it compares the index to 0. Fair enough. It switches on the result. If it's less than 0, then we crash. Yep. If that is equal, then nothing happens, nothing happens. Then we also compare that same index to the length of the array. And if it's less, we don't do anything. If it's equal or greater, then we crash. Fair enough. And then here we get the buffer from the array, which is a pointer. We get the start. We add ints, the start and the index that we want to get. And then we load an item from the buffer of ints from this buffer, add this index. And then we call drop the buffer of ints, please. And that is this one right here. Decrements the counter. If it's 0, then we call drop buffer int items. Makes sense. with the buffer and a cursor which is 0. And then in the end we free the buffer. Seems perfectly fine. So the array thing doesn't happen anymore. This buffer of array of something. But I'm really confused by the set function above. Like, I'm really confused by that. Free the closure, store something. I just don't get this one. Oh, hang on, I do get this one, but not the other one, the array set function. Yeah, array set. There's not even a built-in array set function or something. This is just the... Oh, hang on. Compile array set. And okay, the signature is array set. I was wondering if that is just array get by copy pasting, then I would understand that. Also, I do have this kind of bomb with contains array in here, maybe not. Oh yeah. Dangerous. Alright, go generate array, init array fun, array len, array get, array set, copy buffer fun. We don't even have that. Compile array set, where's that used? Let's look at the mod, maybe. Man. Alright. Yeah, compile array set. Oh, let's call the correct function. Okay, there's actually an error in here for some reason. In line 205, which means in here. Compare ints, len is not in scope. Do need array several times. Yeah, so let's just put the len into, let's extract that And let's store that again. So len is builder dot sub ins well, and start. I think buffer copy is actually a better term for that. And new array. Yeah, no, that's just array. And there's builder.call. I need to. I think that's fine. Builder.drop previous. Yeah, the item type with the pesto. Okay, it compiles at least. That's something. Let's see, we're compiling stuff. That's pretty cool. So then in here we have some member end. That doesn't exist. Let's see, we have, where do we take the member of something? Well, in here for once. Oh, I see, because that's just the length of the array. Yeah, an array only has buffers, start and len. No end. All right. Clean. So some things are incompatible. Oh, yeah, here we go with crashes again, you know. In the pesto, that is. Let's see. We may need another type, I think. Yeah. Well, in the pesto, let's add a new pesto type. Never. Hang on, where's that happening in this switch thing with pesto bodies? Yeah, okay. Yeah. Yeah, here I need to do several things now, like converting yogurt type to pesto. A never type that actually becomes a pesto type, but never. That's pretty cool. Is recursive the never type? No. Oh, let's define a yogurt type anyways. So never is also doesn't also not contain a pointer. that's a tricky one. I guess just that. Taking up no runtime space. Oh, I see. In the builder, in the crash function, we probably map to pesto type this, but it should be pesto type never. And then when in the switch, we also check that the types are the same. But let's also check if t is never, then we'll just continue to the next one. And then here we can say type is type or never, because in case all of the branches diverge, all of them evaluate to never. That's also fine. These are incompatible. All right. Still in compile array set. That would be in the array built-ins. In here. Here we have several switches. Okay, so we have first of all this one, where we finish with crashing. Yeah, and in here this is nothing, and these finish with a message. Here we have even more branches. Oh, look at that, where this finishes with nothing, this finishes with an array, and this finishes with another array. Yeah, this is actually incorrect. I think I want some... Don't I have, like, crashing bodies or something like that? But we finish with nothing. I also want finish with crash. Yeah, that's just going to be builder.crash. Oh, it needs an ID probably. I see. With a builder.string. Yeah, that makes sense, I guess. Now let's do this, but then add a second crash function. with just a string, and that just is builder dot string, and then builder dot crash. Yeah, and then up here we have finish with crashing or something like that. Yeah, finish with crash. Nice. And in the rebuild ends, here we can then simplify stuff. We can say, let's just go through this and look at the crash parts. So this is just bodybuilder dot finish with crash index out of bounds. Clean, simple, short. Oh, reasonably concise. Then there was this one, and that is just builder dot, and let's literally do that same thing below there. And finish with crash, index out of bounds, like that. This is over there, this can be here, indented, beautiful. Then this also be simplified, just with, well, builder dot finish with crash, like that. Oh look, that suddenly the range checks fit on a single screen, even though it is, you know, still not super readable, but better than before. Ampersand finish with nothing. No, that can just be finish with nothing. And then we have this, which will just be finish with crash, range start out of bounds, just like that. Nice. All right. Still the same place, I haven't changed that. Yeah, in here. This should be finished with crash. Yeah, that's unreachable, so don't need to put too much effort into that. Okay, switch cases have different sizes. Now this is kind of back to the original arrow. Oh man. Alright, so we are compiling this pesto expression that calls the built-in crash function with the argument 10. Okay, so we're somewhere where one place returns something and the others crash, probably. Well, yeah. Oh, do I want something like crashing in the waffle as well? Because now suddenly not every waffle has a size and an alignment. Is that what I want? That seems cursed. Somewhat cursed. Huh. I don't know about that. What to do about that? So the cases, they are waffle bodies. I could just not sure. Store something in the body. You know, is there's a crashing body, something like that? And then still have your waffle expressions have sizes and alignments in the general case. Maybe that's a reasonable approach. I have no idea. It seems like not every expression has a size and an alignment, because not every expression even finishes evaluating. But that is kind of ugly, you know. Like in the code, it yeah, I think I'm just gonna stop for today and think about this in the back of my mind, and then someday else continue with that. Okay, I think I'll just add a simple fix in here, which is to just treat a size of 0 as probably coming from a never, so that is always allowed. Yeah, so basically, if the case returns size is larger than 0, and the size is larger than 0, then I want to assert that. Also, like, if this is the case, then the size is just same thing. Alright, so we have size 24. Alignment 8, we have size 24, alignment 8, and we have size 8, alignment 8. Well, yeah, that makes no sense. Where's the last switch in here? Struct int call, and new buffer here. Switch. But we only see IDs. Well, but it is something with a start and a len and buffer. Let me not do that, but instead just print something in the case where we are compiling a function. So this happens while, okay, switch cases have different sizes while waffling array set of array int. look at these. Array set. Yeah. Array set of array of int. Alright, and then here's a switch where one branch evaluates to 24 and the second also to 24 and the third one to 8. That's not this switch, not this switch. Yeah, only this switch remains. So, this one finishes with an array. Yeah, this one too, that's 24 and 24. This one with 8. Yeah. Yeah. What the hell? Finish with crash. Yeah, here. And that just does builder.crash and then builder.finish. Builder.finish takes an ID for its return thing. And the ID is the builder's builder.crash. So the crash function does builder.call built-in of pesto builder.crash. It returns a pesto type.never. Call built-in pushes pesto up call built-in of this thing with nothing. Yeah. Let's look at the code maybe. Array, what is it? Array set. Array len is here. Maybe this one, yeah, array set of this array. Alright, here we have a switch. This returns the never expression, this returns an empty struct, this returns an empty struct. Fair enough. Here this returns an empty struct, this returns never, this returns never. Also fine. Here, this one returns never, this one returns 1, which is this array, this original array. Okay, sure. And this one returns 56, which is also of that same type. Why? That seems reasonable. Switch cases have different sizes. And then here we iterate over cases, which means these are actually the order of these switch cases. AKA this is the one that we have equals, greater, and less sorted alphabetically. So this is equals, greater, and less. What's going on here? array set function. And the code for less. Int. Let's see, we create a 0, we create another 0, we create yet another 0. Then we create this struct, we create another struct, we call a built-in. With the wrong type, by the way. Because this should be UTF-8 bytes. That's the type and the standard library. Yeah. Doesn't explain why this fails though. We have 1, 2, 3, 4, 5, 6 expressions inside, and it returns the last one. Yeah. What's going on here? What's going on there? No. There we go. There we go. Alright. So then at ground, out here probably, and this switch, I assume this is where we're at. Yeah, this is probably Don't placeholder. Yeah, we should only do that if the builder hasn't crashed yet. Otherwise, we don't need to jump there. We have a crash and that's it. All right. Whoa, this is quite cool. So running some program, ran the program, output is this. Assuming the output is a plumb string. Output, hi, drop string. Nice. Now of course, yeah, memory leaked is not super good. Apparently the array is not dropped, I assume. Let's print some more debug stuff maybe. In the heap. Yeah, here. You know, like the heap. That is interesting and all that, but I'm really interested in whether the memory, kind of reusing memory, works. What is this size 80, for example? This would be 16. Yeah, that's 16 plus 64, which is enough space for 8 integers. I am wondering why we free that and then kind of reallocate that and then free that again. This is the output string. Oh wait, we can even check that. We allocate 16 bytes for the lambda that will initialize the array. Then we allocate memory for the array. Yeah, then we free the original the original lambda. We now have an array. And then we allocate memory for the array again for some reason. I don't get that. Let's look at the array set again. Like the index checking, okay, I don't care about that. What I do care about is this part right here. Comparing the ref count with 1. If it is equal to 1, then we just take the array as what we're going to mutate. That's not. But in our case it should be 1 actually. Yeah. Then we go into the greater branch where we create a copy. initialize that, then put that into an array. Yeah. Push another 5. Does that same thing happen again? Okay, so we allocate something at the lambda, an array, we free the lambda, okay. Then we allocate memory again, and again, indeed, yeah. And we only free the last one. If I do that another time, same thing, right? Yeah. So every push allocates more memory for some reason. I wonder why. First of all, let's print the address in hexadecimal. Not that that will fix anything, you know. Not only when freeing, but also when allocating. Well, yeah, like that. Allocate more memory, and we allocate more memory and more memory. Let's compile that with only a single push, maybe. And you know what, let's maybe print the pudding, I think. No, and the pudding arrays aren't even special types, so yeah, this really has to be in the dupe drop free thing, I guess. Let's say we have, let's start with the basics. Yeah, let's print the pudding and clear everything, and then look if the array setting works. And also simplify the example. Just generate, what does list1 do? It actually just generates a list, right? Yeah, like this. Boom, generate a list. List equals that. And then we do list of push. What does that do? In here, it actually does this. So we can simplify that. First of all, let's see if the error is still there. I mean, the array length was never big, so yeah, just take the list.array, aka initialize the sufficiently sized array, aka this right here, and then set an item there. We don't access that. We'll remove this. Boom, this is what we want. Now generate an array of size 8 and then set item number 2, maybe. With set that to 42. I don't know. Alright, yeah, this needs to be imported. Set on an array of t with an int and t. Now this works. Okay, this is interesting. So when we do more of these, does that work? Not only does this work, but also we only allocate the array once. Then those set functions, even though they return a new array, they actually mutate the array in place until at the end we free the original array. Now that is cool. That is really cool. Man. What? That's kind of amazing. Okay, but that means that the error isn't here, but in here somewhere. So here we calculate the sufficiently sized array. And for some reason, the list array len is equal to the list length. Really? Alright, let's look at the compiler output. The pudding. The array set thing, that seems to work. Oh, right, yeah. And do need some failing code for that to see that issue. I mean, let's create a list and then push a single item, I guess. List 1, but push 3 or 2. Let's see where that breaks. So we are compiling some functions. We have the is less than function, we have is greater array.len. we also have the list.push function, where we have the original array in here. We dupe that, we call the length function, which kind of reduces then back the reference count to 1. And then in here we take the length. Call the equals function to check if that is equal to the array length. Yeah. So let's actually look at array len. Some lambda with array set, which looks really promising. Just creates a type and drops that immediately. I mean, sure. And then we call array set with these arguments. Oh yeah, that's a built-in. I see. Where's the main function? I want to look at that too. Okay, so we create an array and we can create a list, right? And then here we call push on that list. Then we drop the list. Okay. But we don't change the reference count of the list any like before that. So all right, so UTF-8 bytes, what's going on here? Oh yeah, that's just a string. Makes sense. Whew, so this is the call logic, basically, the push. Create an int and drop that immediately. Okay, we get the array out of there. And then we dupe that array to get the length. We get the length of our list. We dupe that and we call the equals function. So now by here the reference count of the array should be 1. Yeah. So we switch on whether they are equal. If they are equal, then we need to allocate something new. Otherwise, what should actually happen, we just dupe the array. We dupe this nothing. Yeah, okay, fair. We drop the 6. Which was this bool, okay, fair. We drop this nothing. Oh, here we dupe that. I see, sure. And here we drop that, yeah. Yeah, we can do that. And then in here we take a reference to the array. Yeah. Oh. To the original array. Pseudo array. And then we dupe that and return that. Why do we dupe that? That is I don't quite get that. We push something to this. Here's the I think I know why. Because in here we get the length of the array afterwards. So this at 0 still needs to stay alive until down here, and that 0 also contains the original array. Hang on, if that is true, but it still doesn't explain why that leaks memory. It explains why the code is not as efficient as it could be, sure. But here we dupe the array. Okay, so reference count 1. Reference count 1 is moved to reference count of 2. Then in here we get the length. Okay, sure. We dupe that. Sure. And then we call array set using that newly unique array that is now no longer unique. And that int and then the item. Huh. True. Although I'm like, I'm wondering, like, do we? So we still have one ownership of this array, basically. The 0. But here when we drop the 0, that should also drop the array. So this is dropping something of this type. Array being an array of t and the length being, well, something. So dropping that struct where's the drop? Drop. Oh, right, there are no drop functions yet. That makes sense. Huh. No, not entirely sure what to do about that. I mean, okay, later on in the pesto, we indeed have drop functions. For example, we get the array out of there, and then we call drop of that array. And then we take the length and do nothing with that. So calling drop on an array, I saw that somewhere up there. Here. And that gets the buffer out of that array. Calls drop buffer. Here we are. Yeah, that decrement is the reference count, and if that's 0, then it does some stuff. Yeah. Well. I don't know. But it seems like for the case where the array is where the reference count is greater than 1 and the array is set, something is not correct here. We allocate a new buffer, sure, and then we compile that buffer, put that into an array. Oh, yeah, and we drop the original one. That makes total sense. Alright, yeah. Builder dot, what is it, drop buffer? Of the original array. This is the kind of thing where the fix is one line of code, but finding that one line just took like half an hour. Yeah, that's not it. Yeah, that's not it. The original buffer is not free. Oh, no, not free, but drop. No missing memory allocations that get missed for going out of scope. No leaking memory. Everything just works. And let's try to make that reuse the old memory. And I know this is hacky, but let's see, why didn't this work before? Because here we access the list. The original list. And that means that in here we don't have in here in this set function that list.array is, well, the list is kept alive until here, so we can access the len. So this list down here also, we could also access the array down here. We don't, but the list is still kept around. So this is also another reference to the array that is kept around. So then this sufficiently sized array.set actually doesn't have exclusive ownership of the array, so the array is copied. Let's instead do this. Get the list length up here. And again, this is hacky. I would do this. Maybe it makes sense to have some sort of compilation pass that if there's a struct available, it just automatically kind of explodes, or it desugars that into the individual struct members right at the at the top of the scope. And then down below, when you access individual members, you only access these members actually. Like this behaves like I told it should behave, but that's not how I want this to behave. Yeah, because then in here we can just say len. And hopefully at this point the array is no longer, dot len. Yeah, that's true. And that is like the array, I guess, list len. Oh yes, oh yes, that is pretty cool. No more allocations. Let's see, list 1, push 2, push 3, push 4, push 5, push 6, push 7, push 8, push 9, I don't know, something like that. And what should happen is, look at that, we have allocated 80 bytes here. And then I don't quite know what this is. Oh, this is probably the lambda for copying the array, or something like that. That is super cool. That is so cool. Oh man. That's crazy. That is crazy. Man. Whoa. Let's go beyond beyond 16 maybe. Let's say list of 1, 2, 3. And still the same thing, but that's cool. Yeah, I think that's a nice note to end on. Arrays work. I mean, in general, in the last couple of videos, like these were kind of like tightly connected features, bytes and arrays, and then based on that strings, and based on strings again crashing, which is used by arrays again, and everything kind of fits together now. But this is pretty cool. You know, having like array lists in the language, in the standard library actually, in a fully functional language where data is immutable. The push function, again, like this is crazy. The push function takes a list and an item and it returns you a new list. But then it checks the reference count, and you see that it only allocates like a few lists here. That's super cool. Yeah, I guess that's I'm happy. That's it for today, and see you in the next video. Bye.